So in this video, we're going to look at the idea of free body diagrams as a way of visually representing the forces that are acting on an object. We oftentimes in physics use diagrams to illustrate things, and the free body diagram is a really great diagram because it actually shows some of the science behind what's happening in a physical situation, but at the same time still shows it in a visual way that's kind of easy for people to understand without having to do any math. Now, there is a little bit of math to free body diagrams in the sense that the length of the arrow represents the magnitude of the force. So, for example, let's say that I drew an arrow pointing to the right, and I said that this arrow had a value of 10 units. We'll talk about the units in just a minute. I could show that a force was stronger than that force, let's say double the force, by showing an arrow that was twice as long. And there's not a lot of math to this, but this is a way for you to show that this force is stronger and actually show a mathematical value of how much stronger that force is. And then the second aspect of using these arrows to represent forces is that the arrows point in the direction that the force acts. So the direction of the arrow represents the direction of the force. And I can point that in any direction that I want and stretch out the length of the arrow until it's appropriate compared to the other forces that are acting on that object. So that's the basic idea behind free body diagrams. I'm going to show you forces individually before we go to a full free body diagram because it's kind of a lot to take in. And so in order to think about how to draw the free body diagrams, it's really important for you to understand what are the main forces that you would encounter in your daily life, or things that you might see that you have seen for the most part in your life. Now we're going to avoid most of the invisible forces like electric force, the magnetic force, the nuclear force. We will look at one invisible force, and that is the first force that we're going to look at, and that force is called the weight. So the weight is a force that is exerted by gravity, and actually I'm going to add that word, the force of gravity. It's completely accurate when you talk about the weight to refer to that as the force of gravity. This is the reason why the two words sort of exist. When you talk about the force of gravity acting on objects like you or me or like a car, even huge objects like a mountain or a building or something like that, but something near the surface or at the surface of a planet, then we're going to usually refer to the force of gravity as the weight of that object. So we'd say my weight, or the weight of the building, or the weight of the car. If on the other hand, we're talking about the force of gravity extending beyond just the surface of the planet, but out to other planets or other worlds or other moons. Like, for example, the Earth exerts a gravitational force on the moon. Now, I don't think I would refer to that force as the weight of the moon. That doesn't really seem like it's measuring things fairly compared to things on the surface of the Earth, because the value of gravity at the location of the moon is much, much less than it is here at the surface of the Earth. It's technically, you could think of it as the weight, but normally weight is going to be referred to the force that's exerted on all objects with mass near the surface of a body, like near the surface of Mars. We could say, if I went to Mars, I would have a weight. It would be different than my weight here on the Earth, but I would still refer to it as weight. Whereas when I think about the force that the Earth exerts on Mars itself, I would probably refer to that as the force of gravity. So this is the only force we're going to look at today in which there's an actual equation that you can use to calculate the value of it, and it kind of illustrates how forces are calculated. So weight, which is a force, is equal to the mass times the acceleration that's caused by gravity, and that of course would be little g. So each of these three variables, W for weight, M for mass, and G for the acceleration of gravity or the gravitational field strength, these three variables produce the first force, which is weight. And we can look at an example of that. One thing I just want to point out, there's a little sort of weird thing, and that is that the unit for calculating force in the metric system uses the kilogram rather than the gram. Essentially, the gram was just a little bit too small, so Newton made a sort of an executive decision that he would base the calculation of force on kilograms rather than on grams because the gram is just too small. So an 80 kilogram man, that would be 80,000 grams. So that's really not a very convenient unit to use. So in the metric system, the unit for force is called the Newton. It's about a fifth of a pound, so it's a much smaller unit of force than the pound is. And the way you calculate it is by doing mass, which is going to be in kilograms, times the acceleration, which will be in meters per second squared, to give us this new complex unit called the kilogram meter per second squared. Now you rarely have to say that, but it's important that you understand that inside the Newton, hidden inside of Newtons, is these units, kilogram, meters, and seconds. And we're going to see several other combinations of kilograms, meters, and seconds. So really important that you can look at an equation and think about the units that are going to be created by these two properties, and then therefore put that all together to come up with the units for the overall property, which in this case is the kilogram meter per second squared. So let me just bring this up just a little bit more. Let's go ahead and make this calculation. So an 80 kilogram man, the value of G at the surface of the Earth is 9.8 meters per second squared, but we're going to use 10 as an approximation. It's very close. It's only off by a few percent from the real value of gravity. And that means that an 80 kilogram man, which is very average mass for a man, would be 800 newtons. So that's a little bit of a different thing to think about. You're probably used to thinking about weights like 100, 150, 200 pounds. But in newtons, since newtons are much smaller than a pound, only about 1/5 of a pound, the numbers are going to be much bigger. And I would have an expectation that you would become familiar with that you would know that the weight of human beings, adult human beings, is probably somewhere between 500 to 1,000 newtons. And then obviously, therefore, the mass for things like a car is not going to be in the thousands of pounds, but it's going to be in the tens of thousands of newtons. So that's something that you just kind of have to get used to, and you'll get accustomed to as we do more and more practice problems, and you see different weights being calculated for different objects, different sized objects. So that's the first force that we're going to talk about, which is, again, the weight of an object, or it can also be referred to as the force of gravity. Let's look at another force that oftentimes interacts with the force of gravity, and that is the normal force. This is a little bit of a strange one. The word normal in physics actually means perpendicular. So I'm going to put the little perpendicular symbol above the word normal. That's an unusual use of the word normal, but in physics, it always refers to something being perpendicular. So this is literally the perpendicular force. It's also sometimes called the reaction force, because this is the force that surfaces exert on each other. So for example, I can push on the surface of this paper and I can feel the paper pushing back on me. That's because this paper is a solid surface. So anytime something comes in contact with it, it's going to be likely to push away from itself. And that's one of only two forces that the surface can exert. It can push away from itself, that's a perpendicular force, or you can have something slide along the surface of the thing, and then as a result of that, you'll get frictional force. And so that force will be parallel to the surface. One perpendicular force, one parallel force. The normal force is reserved specifically when we have two solid objects. So if you had like a cup of water and you thought about the force at the bottom of the cup, between the water and the cup itself, we would not refer to that generally as a normal force. The normal force is when two solid objects are being exerted against each other. So just to give you some different examples of how the normal force would look, if we take a very simple situation like a box resting on a flat surface, the normal force is going to come, there's two normal forces actually, one from the box and one from the ground. The ground cannot reach out and grab the box, it cannot push sideways on the box. All it can do is exert a force that points directly away from its surface, perpendicular to its surface. I could draw the little right angle symbol there to show that the force is perpendicular to the surface that is creating the force, the surface that is exerting the force. If we take this whole surface and we tilt it sideways, so we put this on a ramp, a fancy word for a ramp is an inclined plane. So plane meaning a flat surface that we can put something on, and inclined meaning tilted at an angle. Then you would see that the normal force also tilts over, because the normal force, again, is always going to be perpendicular to the surface. So as I tilt this thing further and further up, I'm going to see that normal force moving right along with it, becoming more and more shallow of an angle. And as I tilt it back to a flat plane like this, I'll see the normal force going back to being vertical if I go back to this. Now, the normal force is frequently points upward, but it does not always point upward. So on inclined planes, or if you imagine if I push against the side of a wall, if I push against the ceiling, the normal force does not point down. It simply points away from the surface. A kind of unrelated force is the tension that sometimes acts on objects. And tension, unlike the normal force, which is the normal force is always a push force, the tension is the opposite of that. It's always a pull force. It is always pulling towards the center of the object that is under tension. That could be anything. I mean, anything that is pulled or stretched is technically under tension, but we're mostly going to address situations in which we have strings or ropes, cables. Springs can be stretched, so therefore they can also be under tension. And as I said, the tension is always a pull force, and it always points along the length of the string. So let me give you an example so we can make that maybe a little bit more concrete. Let's take the same box that we looked at in the last example problem, but in this case we're going to tie a string to it. And I'm going to put a person here. So the person is reaching back and pulling on this string. So there are actually two tensions here, because not only is there a tension acting on the box, because the box is connected to the string, and the string is always pulling towards its own center. So that means on the box, that force is acting to the right. And we can label that as T, or we can also label it as F of T. When you see these, either the F of N or F of T, that's the way you would pronounce it. F of T or F of N, or whatever letter is down there. You could say F of N, or you can say normal force. You could say F of T, or you could say tension. It's the same thing. It's just a matter of whether you're referring to the force according to the symbol that's commonly used to symbolize it, or whether you're actually saying the name of the force. So I could say T for tension, or I could say F of T also for tension. Either one of those would be acceptable ways of expressing that force. The tension also is pulling in the opposite direction. So I see 2 points, one right here where it touches the guy's hand, and one right here where it touches the box. Each of these two things experiences that tension, but it points in opposite directions. So strings are, in a sense, always pulling towards their own centers. They're always pulling things towards their own, the center of themselves. So those are two forces that are very common. You can think of lots of examples of normal force. I'm sure you've seen tons of examples of strings or ropes or cables that were being pulled or being used to hold something in place or to move something. So now let's move to a force that is a little bit different. This force is called the frictional force, and I'm not going to go into a great deal of detail here because we'll talk more about the frictional force. This is a really, really important force. This is really the force that caused so much confusion among early scientists or early philosophers, people who tried to figure out how do forces work? How does it, what causes objects to move in the way that they do? The frictional force really made it difficult to understand. The frictional force is when two solid objects slide against each other, or they try to slide against each other. It's caused by irregularities in the surface, but then also there are small electric charges because of the way electrons are distributed within a molecule. Even though there are equal number of positive charges and negative charges, they don't have to be distributed evenly, and in most molecules they are not distributed evenly. And so that means that one side of the molecule might be a little bit more negative while the other side of the molecule is a little more positive. Even though overall the molecule is neutral, it will still exert electric forces on surrounding molecules. So molecules in the two surfaces, when they get close to each other, very small electric forces also participate, and that's part of the source of the frictional force. For our purposes today, the most important thing for you to remember is that it always opposes the motion or the intended motion. So for example, if I take this domino and I give a little push on the side of it, it doesn't move, but I am exerting force on it. I'm pushing very gently against the side of it and it's not moving. But that's because there is a frictional force acting on it. So if I try to push on the domino in this direction, then the frictional force is going to oppose me in this direction. If on the other hand, I come over on this side and I start to push the domino down in this direction, the frictional force now points in this direction. When I push this way, the frictional force points in this direction. So no matter what I do, whether the object is actually moving or not actually moving, if I am putting a force to it, I'm trying to make it move, then there is going to be a frictional force, and that frictional force is always going to oppose whatever direction of motion that you're attempting to move the thing along. So let's take a real quick look at the example that we were just using in the last force, tension. Let's get rid of the rope, and instead of having the person pull on this thing, we'll have them do the opposite. We'll have them push on the box now. So it does not matter, I cannot stress enough, it does not matter whether the box is actually moving or whether the box is at rest. If somebody is pushing on this, then there is going to be a frictional force, and that frictional force is going to oppose the motion. So based on the way this person is pushing, which is to the right, that means that the frictional force would have to be to the left. and that is capital F and then lowercase f. So the force of friction, or F of F, or the frictional force is also equally fine. Let's say, for example, just imagine this. We take that box and put it back on the inclined plane. If you remember, one of the forces that we looked at was the normal force. And in this case, the normal force would be perpendicular, like this, coming from the surface outward, pointing perpendicular to the surface of the ramp. But there's a second force, and that second force is the frictional force. Now you have to think for a second, which way, if I let this box go, which way would it move? Would it move up, down, left, right? Is it going to move at an angle? I think it's fairly clear that the box would start to slide down the ramp. I'm sure you've seen thousands of examples of something sliding down a ramp. You may have been on a slide, which is exactly what we're talking about right here. Now, when you're on that slide, there is a little bit of a frictional force, but because you are trying to move in this direction, in the downward direction, that means that the frictional force in this example would point upward. So the frictional force is always going to oppose either the actual motion, if the thing is in motion, or the motion, the direction of the motion that it's trying to make. In this case, even if the box is at rest, there is a frictional force, and because the box is trying to move down and to the left, the frictional force is going to oppose it. Now let's just imagine for a second that we took this guy from this example over here, and we brought him over here and had him start pushing on the box upward. As he begins to push upward on the box, this frictional force is going to decrease because the frictional force is not needed to hold the box in place. And if that person continues to push harder and harder, what will happen is that frictional force will get smaller and smaller and smaller and smaller until eventually it will disappear. And then if they continue to push even harder, the frictional force will flip around and start pointing in the opposite direction as the person begins to start pushing the box up the ramp. So the frictional force on a ramp is not always pointing up like this. It's just in this particular situation, because there are no other forces acting on it, the box wants to move downwards, so the frictional force opposes that. If, on the other hand, somebody pushes the box up the ramp, then the frictional force is going to flip around and point in the opposite direction. The frictional force is really a tricky thing. When this person pushes on the box, the frictional force is there. When they let the box go, if the box comes to a stop, once the box is stopped, there's no more frictional force acting on it. So this is a force that can come up and go away. It's a little bit like a reactionary force. It's a little bit like the normal force. It will react to whatever the situation that it's in. A very similar force, not quite the same thing, but very similar force, is a force called the drag force. And what's different about the drag force compared to the frictional force is that it's not based on having a solid surface. So when a solid object moves through a fluid, and a fluid is either a gas, like the air in the room that you're in, or a liquid, like water in a swimming pool, it's like friction in the sense that it always opposes the motion of the object. But one thing that is different about it is that you must actually move. So when I move my hand back and forth like this, I can feel the air. And I'm sure that if you move your hand back and forth right now, you can feel the air. So as I move my hand across like this, there are air molecules in this part of the air in front of me. And as I move in this direction, they've got to get out of my way. So as I move my hand like this, I knock molecules out of the way. If I move my hand faster, I knock even more molecules out in less time. And so therefore I feel even more force. I would certainly never tell you to put your hand out of the window of a moving car. You should never do that. But I'd be willing to bet that you have already done that and you felt the drag force. That's a great example where you would have felt the drag force. Don't ever do that, by the way. Don't ever stick your hand out of a moving window. That's a really dangerous thing. You can easily lose a hand by not noticing that something coming up on the side of the road. But I'm sure that most of you have done it, that you have put your hand out, or even on a bike, you've put your hand out and you felt the drag force, or when you're riding your bike, you can feel even when there's no wind, you can feel the air because you are moving into the air molecules and knocking them out of the way. Now, that means that you must move. So unlike the frictional force, where you can just have the intention to move, it's not enough to intend to move. In order for the drag force to really be felt, you need to actually move. There's lots and lots of examples. When you try to walk through a swimming pool, you're in the shallow end of the swimming pool and you try and walk, and it's really difficult. That's the drag force, because there's water molecules in your way. They need to get out of your way in order for you to walk by. And so as a result, you experience the drag force very dramatically in that situation. One place where I'm particularly going to kind of focus on is an airplane. And the reason that I want to focus on the airplane is because there is no frictional force there. in terms of the outside of the airplane. The airplane is not rubbing against any solid surface, so therefore there is no frictional force, but there is a drag force. And if we assume that the airplane is traveling in this direction, a velocity to the right, then that means that the drag force will oppose it moving towards the left. So drag force and the frictional force, because they are so similar, because they both are based on resistance to either a solid surface or to a fluid, oftentimes we combine them together. You know, when we talk about an airplane, I would call that the drag force. But when we talk about a car, let's say that you're sliding down a slide. Well, you have the frictional force. That comes from your seat touching the slide. And then also you have to have air molecules out of your way, so then there's also drag there. So in situations where there is both a drag force and a frictional force, most of the time we're just going to combine those together to call them the resistive forces. That's where the F of R comes from. The idea of calling it the drag force, or F of D, is just an abbreviation for drag force, or F of R, the resistive force, the force that resists your motion, and that can be either friction or drag. So then moving away from the resistive forces, more positive forces, forces that allow you to do things, one would be the buoyant force. So the word buoyant refers to floating, and I'm sure some of you maybe have heard that word before. You know, in English we use that word oftentimes not so much to mean like physically something floating, but that you're lifting something up. So for example, if you went to the hospital to see a friend who had been sick, we might say that you buoyed his spirits, or his spirits were buoyed by your visit. And so it just simply means lifting. It's a form of lifting. In this particular case, it's caused by density. So when you have two objects of different density, they're going to experience a significant buoyant force. Now, technically, any object that is placed in a fluid is going to experience some upward force that is caused by the differences in the density and the fact that some of the fluid is displaced. Anytime fluid is displaced, there is a buoyant force. Now, when would we be most interested in this buoyant force? The main place where we would be interested in it is when the buoyant force is greater than the weight of the object. So a good example of that would be a boat. So in the case of a boat, I know that looks a lot more like a candle than a boat, but we'll pretend like that's an actual boat. So there's an upward force on the bottom of the boat that comes from differences in the density of the boat compared to the difference in density. And in this case, the density is great enough, that is to say that the boat, even though it might be made out of metal or wood or whatever it's made out of, it has overall lower density than the water, and therefore it floats. So in that situation where the density of the object is less than the liquid or less than the fluid, then you're going to see the thing float. Now, if it let's say, for example, like you throw a brick into the water. Well, a brick is not going to float, but it will still feel a buoyant force. It will not fall at the same rate as it would if you dropped it in the air, because the air produces much, much smaller buoyant force than the water produces, because the water is so much more dense. So when you drop a brick into the water, it displaces so many more molecules than it does when it's in the air, because the air is mostly empty space anyways. It will sink, the brick is going to sink to the bottom, but it wouldn't sink as fast as it would have if you had dropped it in the air, because of the buoyant force, because of how much stronger the buoyant force is. So everything doesn't have to float in order for there to be a buoyant force. All objects that are placed in a fluid are going to experience a buoyant force. But two objects that we'll be really focused on when we think about the buoyant force would be like boats or anything that floats in the water. It could be like a piece of wood or something like that. And then hot air balloons. So each of those would experience a buoyant force, which has to do with the differences in the density compared to the outside material, the outside fluid. That is very different than the way that airplanes fly. So airplanes do not float. They do not use the buoyant force. There are airships. They're called zeppelins or blimps, sometimes they're called. And they use generally like a lighter weight gas, like helium or hydrogen, so that their density will be lower than the air, and that allows them to literally float, so they don't fly. Airplanes don't do that. Airplanes produce their upward force, that is called lift, which we'll usually refer to as F of L or F of lift. The lift is caused when the air flows over the wing. So as air flows over the wing and under the wing, it causes, because of the shape of the wing, it causes higher pressure on the underside of the wing than it does on the top side of the wing. And because the pressure is so much greater on the bottom side of the wing, it actually starts to produce lift that causes the upward force that is exerted on airplanes. So it does not matter whether it's a fixed wing aircraft, like airplanes, or a rotating wing, like on a helicopter. Helicopter blades are shaped exactly like the wings on an airplane because by spinning the rotors around or spinning the blades around, you cause air to flow over the wing, and as a result, it produces lift. So, I mean, fundamentally, the airplane and the helicopter are the same device in the sense that they produce the lift in the same way. They produce these pressure differences above and below their wings that causes an upward force that is what allows the airplane to stay in the air. So I'm going to draw, again, the airplane. This is the best example for sure of lift that you would think about, something that you see every day passing out. Passing over our school. We live very close to Midway Airport, and so we see planes flying in all the time, taking advantage of that lift force. Planes obviously need more than just lift. How do you get the air to flow across the wings of the aircraft? Well, you need to make the aircraft move, so that's where the engines come in. The engines propel the aircraft forward. One thing really important to understand about the thrust force is that the thrust force is something that the device or the person or the object can do on its own. So we looked at an example where we pulled a box with a string. We wouldn't call that the thrust force because that's not something that the box did itself. Now, if the box had a little motor with wheels connected to it and we could turn that motor on and the box could move, then that would definitely be a thrust force. That would have nothing to do with any outside person acting. That's just the object itself. So a person, for example, can produce a thrust force, and the way they produce that thrust is by pushing against the ground. You could put a person on a skateboard and the person can push against the ground, and therefore, again, it will cause the object to begin to move forward in the direction that they want to travel. So I'm going to show several examples. I'm going to do one thing different with the airplane this time. And that is we're going to put an engine under it. So in this case, the thrust is produced by... you can spell the word out, just like up here we could say lift or we can say F of L. It's really, in general, I would say you can use the abbreviation as long as it's clear from the drawing or from the explanation of what the object was, what we were talking about. So if they talk about airplanes and you draw an arrow pointing upward and you say that's F of L, I completely agree. That makes complete sense. I would assume that you are referring to the lift force. Same thing for the thrust. Now you have to be a little bit careful about the F of T though, because that's also used sometimes for tension. So then that could actually create confusion. For me, normally when I say F of T, I'm always referring to the thrust, but not always. There are times where I use F of T in certain situations. And so you really have to just take it from the context of the problem. If I asked you about an airplane and you say F of T and it points in the direction the plane is moving, I would assume that what you meant was you're talking about the thrust force. The thrust force is always in the direction of the motion or the intended motion. So for example, we could have the airplane be on the ground. We can get the engines going with the brakes on so that the plane cannot move forward. There's still thrust, but it's just not causing the plane to move forward yet because there's another force acting against it to prevent that from occurring. So let's take a quick look. Let's just run through a few of the possible ways in which these free body diagrams will be put together. We'll look at several different situations. And then that should give you enough of an idea for you to start drawing your own free body diagrams and labeling them correctly. So let's look first at an example where we have a person pulling a sled across the ground. And I'm going to draw kind of an old school sled. It says that the sled is being pulled using a rope that makes a 35-degree angle to the horizontal. It's something about like this. Oh, sorry. Put a little circle right there. So here's a person pulling the sled across using a rope. Now, obviously, what you're going to see is going to be a little bit difficult about this drawing is that sometimes it's hard to draw the forces because you have to literally draw them directly on the picture. So you're drawing a pencil line on another pencil line. Obviously that's difficult to see that those are two separate lines. So it is very difficult to do. Obviously clearly there's a rope, so there is clearly tension. So you can draw the tension right on the rope. There is clearly a frictional force. Now this is being pulled across the snow, so there's not a lot of friction, but I wouldn't say there's no friction. There's a very small frictional force. Where is that frictional force? It's right here between the two surfaces. You can see how difficult that is to draw. I'm drawing a line on top of something that is already a line to represent the drawing of the actual physical object. There is a normal force. The normal force comes from the ground pushing up against the bottom of this thing. And then that leaves one last force. There's no thrust force because this ice device cannot produce thrust. There's no lift. There's no buoyant force. There might be a little bit of drag force, but I'm going to count the drag force as part of the frictional force. So we'll just count that as part of the total frictional force. And so that really only leaves one other